So after discussing homogeneous functions, let's move on to homogeneous first order differential equations. So a differential equation of the form m of xy dx plus n of xy dy equals 0 is said to be homogeneous if the two functions m and then n are homogeneous functions of the same degree. Now what this primarily means is that let's assume that if we take this function m of xy, if each term of m of xy has a degree of 1, and then if each term of n of xy also has a degree of 1, then we say that the two functions are homogeneous functions of the same degree. Now, considering this differential equation, let's try to make dy dx the subject, or better still, let's try to put this differential equation in the standard form. So what we are going to do is we are going to transpose this term to the right hand side. So we are going to have n of xy dy equals negative m of xy dx. So at this point, we divide through by dx by dx and then by n of xy. So we cancel out this and then that, and then we also cancel out this and that, so that we have dy dx equals negative m of xy divided by n of xy. Now, since the two functions are said to be homogeneous functions of the same degree, then it means that we are going to pull out lambda n over lambda n. Now, in the previous video on homogeneous functions, we explained this. So if you don't understand, kindly go back to the previous video on homogeneous functions. So we are going to have negative m of xy divided by n of xy, and that is equal to dy dx. Now, since the two functions are homogeneous functions of the same degree, it means that the value of n is going to be same for the two functions m and then n. So at this point, we can simplify this differential equation as lambda exponent n minus n, and then in place of this whole thing, we are going to have the function f of xy. Now we can simplify this as lambda exponent 0 times f of xy, and that is equal to dy dx. And then we know that any non-zero number raised to the power 0 is equal to 1. So we can have this to be 1 times f of xy. And then alternatively, we say that the differential equation given of the form dy dx equals f of xy is said to be homogeneous if the function f of xy is a homogeneous function of the degree n equals 0. So in summary, a differential equation given of the form m of xy dx plus n of xy dy equals 0 is said to be homogeneous if the two functions m and n are homogeneous functions of the same degree. And then the differential equation dy dx equals f of xy is also said to be homogeneous if the function f of xy is a homogeneous function of the degree n equals 0. So now let's move on as we solve a couple of examples. So this is example 1. Let's try to solve this example together. So we are going to solve the differential equation x squared plus y squared all times dx minus 2xy dy equals 0. So we have the differential equation x squared plus y squared all times dx minus 2xy dy equals 0. Now this differential equation is given of the form m of xy dx plus n of xy dy equals 0. So by this we say that m of xy is equal to x squared plus y squared, and then n of xy is also equal to negative 2xy. Now, the first thing we need to do is to check if the two functions are homogeneous functions of the same degree. So for the first one, m of xy, now for this term, x has a degree of 2, and then also for this term, y has a degree of 2. Now, since the two terms have a degree of 2 each, it means that this function is a homogeneous function of degree 2. Now let's move on to the second one, n of xy. The degree on x is 1, the degree on y is also 1. Now, since we have the product of these two variables, then we are going to add their exponents. So 1 plus 1 is equal to 2. Therefore, this function also has a degree of 2. Now, since the two functions have the same degree, we say that they are homogeneous of the same degree. So this differential equation is a homogeneous differential equation. Now let's try to solve this differential equation. So we have the differential equation x squared plus y squared all times dx minus 2xy dy equals 0. At this point, we are going to put this differential equation in the standard form. So we transpose this term to the right hand side. So we are going to have x squared plus y squared all times dx equals 2xy dy. So we divide through by 2xy dx, 2xy dx, and then we have this cancelling out this also cancels out this, and then we are going to have x squared plus y squared over 2xy, and that is equal to dy dx. So at this point, this differential equation is not of variable separable type. Now, to make it separable, we need to put in two substitutions. Now, the first substitution is y equals v times x. That is the first one. And for the second one, we are going to differentiate this function with respect to x. Now, notice that v here is a function of x. So we are going to differentiate this function. That is going to be the second substitution that we are going to make. So we have dy dx equals, now we are going to apply the product rule here. So we hold v and then we differentiate x with respect to x, which is 1, plus we hold x and then we differentiate v with respect to x, and that's dv dx. Therefore, we have this to be v plus x dv dx. So we are going to substitute these two into this differential equation, and at the end we are going to obtain a differential equation which is of variable separable type. So let's do that. So for dy dx, equals x squared plus y squared over 2xy. For dy dx, we have v plus x dv dx. So that's going to be v plus x dv dx equals x squared plus, in place of y we have vx, so vx all square divided by 2x times vx. Now let's simplify this. So we have v plus x dv dx equals, we have x squared, let's work out this becomes v squared x squared all divided by, we are going to have 2 times x squared v. Now let's transpose v to the right hand side. So we have x dv dx equals, at the numerator we factor out x squared. So x squared, inside of the bracket we have 1 plus v squared all divided by x squared times 2v, okay, and then minus v. So we have x div dx equals x squared cancels out x squared. We are left with 1 plus v squared over 2v minus v over 1. So let's try to find the LCM. So LCM between 2v and then 1 is 2v. Now 2v divided by 2v is 1. 1 times 1 plus v squared is 1 plus v squared minus 2v divided by 1 is still 2v. 2v times v is 2v squared equals x div dx. So we have x div dx equals 1, and then here v squared minus 2v squared is negative v squared. So we have 1 minus v squared divided by 2v. Now we have x dx here, and then we have 1 minus v squared over 2v. So let's transfer div to appear at the denominator. So that's going to be x divided by dx equals 1 minus v squared divided by 2v times div. Now at this point, because we have the x div both appearing at the denominator, we are going to flip both sides of the equation so that we have the x and then div appearing at the numerator. So that becomes the x over x equals 2v div over 1 minus v squared. Now at this point, we've been able to separate all x's on one side and all v's also on one side. So at this point, we are going to perform our integration. So we are going to integrate both sides. Now the integral of 1 over x is ln of absolute value of x, and then whenever you do integration, you have a constant appearing. So instead of writing c, to make everything simple for us, we are just going to write ln of c. So that is on the left hand side equals. Now on the right hand side, we have the integral of, so first let's pull out 2. So we have 2 on the outside, the integral of v div divided by 1 minus v squared. Now we are going to use u substitution. We are going to integrate this by u substitution. So first we let u be equal to the denominator 1 minus v squared, and then we differentiate u with respect to v, and that is equal to, this is a constant, it goes to 0, negative v squared becomes negative 2v. Now let's make div the subject. So we have div equals, we interchange the positions of these two values. Div goes here, negative 2v comes here, so that becomes du divided by negative 2v. Now let's substitute u and then div in here. So on the right hand side, we are going to have 2 times the integral of v times, we have div to be du over negative 2v divided by u. Now this becomes 2, we pull out this, so 2 divided by negative 2, we have the integral of v cancels out v, and then this becomes du over 1 times 1 over u. Okay, so we can simplify this as du over u. So this goes to negative 1 times, when you integrate du over u, then you have ln of the absolute value of u. So this becomes negative ln of, we have u to be 1 minus v squared. So that is that, you have negative ln of absolute value of 1 minus v squared. So that appears on the right hand side. So negative ln of absolute value 1 minus v squared. Now negative ln of absolute value of x is equal to ln of the absolute value of 1 over x. So we are going to apply that here on the right hand side. So that's going to be ln of the absolute value of 1 over 1 minus v square. And then on the left hand side, because we are adding these two ln values, it means we are going to multiply x and then c. So we have ln of absolute value xc. Now because we have log on both sides, we do away with the log, and then we have xc equals 1 over 1 minus v square. Now remember that y was equal to vx, okay, and so if you want to find v, then v will be y over x. So we are going to substitute y over x in place of v. So this becomes y squared. Because it is v squared, it becomes y squared over x squared. Now let's cross multiply, okay, or let's better still interchange the positions of these two values. So it's going to be 1 minus y squared over x squared equals 1 over, and then xc comes here, xc. Now since we have the denominator of this fraction to be x squared, let's multiply each term of this equation by x squared. So we have this by x squared, and then we have this by x squared. So let's multiply x squared across. So x squared times 1 is x squared minus x squared times y squared over x squared. X squared cancels out x squared. We are left with only y squared. So minus y squared equals, x cancels one of the x's here. So we are going to have x times 1 over c. Now 1 over c is a constant. So let 1 over c be equal to c1, which is also a constant. Therefore, we have this to be x squared minus y squared equals x times c1. Now this is said to be the general solution of the differential equation. General solution of the differential equation. So now let's move on to the next example. Now to example 2, we are going to solve the differential equation xy y prime equals 2y squared plus 4x squared with initial condition y of 2 equals 4. So we have the differential equation xy times y prime equals 2y squared plus 4x squared. Now first of all, let's try to make dy dx the subject. So that becomes, we have xy, y prime becomes dy dx, that is equal to 2y squared plus 4x squared. Now we divide through by xy, and then we have dy dx equals 2y squared plus 4x squared, all divided by xy. Now for the function on top, we have the degree on y to be 2. We have the degree on x for this term also to be 2. Therefore this function, the function on top, is a homogeneous function of degree 2. Now to the function at the bottom, we have the degree on x to be 1, degree on y also to be 1. Because the two variables are multiplying each other, we are going to add their exponents. So 1 plus 1 is 2. So this function also has a degree of 2. Now since the two functions are homogeneous functions of the same degree, it means that the differential equation is a homogeneous differential equation. So now let's proceed with the solution. So first of all, we need to make the two substitutions. So first, y equals vx, and then second we have dy dx equals v plus x dividing dx. So let's substitute y and then dy dx into this differential equation. So on the left hand side, we are going to have v plus x dividing dx, and that is equal to, on the right hand side we have 2 times, in place of y we have vx, so all square, plus 4x squared, all divided by x. In place of y, we have vx. So we are going to have v plus x div dx equals, this becomes 2v squared x squared plus 4x squared, all divided by x squared times v. Now we are going to transpose v to the right hand side. So we have x div dx equals, at the numerator we can factor out x squared. Inside of the bracket we have 2v squared plus 4, all divided by x squared times v, and then this becomes negative v over 1. So we have x div dx equals, we cancel out x squared, and then we can find the LCM between v and then 1. LCM between v and 1 is v. So v divided by v is 1. 1 times 2v squared plus 4 is 2v squared plus 4 minus v divided by 1 is v. v times v is v squared. So here we are going to have x div dx equals, let's simplify this. So 2v squared minus v squared is v squared. So we are going to have v squared plus 4 all over v. So at this point we have x div over dx. So let's transfer div to appear at the denominator here. So that becomes x over dx equals v squared plus 4 over v div. Now let's flip two sides of the equations so that we have dx over x equals v div over v squared plus 4. Now at this point we've been able to separate all x's on one side, or put all x's on one side and then all v's also on the other side, so we can perform integration. So we are going to integrate both sides of the equation, and then integral of 1 over x dx, we are going to have ln of absolute value of x plus the constant ln of c, ln of absolute value of c, that is equal to the right hand side. Now let's work out the right hand side. So on the right hand side we have the integral of v div over v squared plus 4. So we are going to use u substitution. Okay, so we let u be equal to the denominator v squared plus 4. Now we differentiate with respect to v, so that becomes 2v. This is a constant, it goes to 0. Now we make div the subject, so div is equal to, we interchange the positions of these two so that we have du divided by 2v. So let's substitute div and then u into this integral. So we are going to have the integral of v times div is du over 2v, all divided by u. So v cancels out v. We are left with the integral of du over 2 times, this is u over 1, so it becomes times 1 over u. So we simplify this as du over 2u. So 1 over 2 is a constant, so it comes outside. Then we have the integral of du over u. Now when you integrate 1 over u with respect to u, then you are going to have, so we have the half times ln of absolute value of u, and that will be equal to 1 over 2 times ln of absolute value of u is v squared plus 4. So that is what is going to appear on the right hand side. Okay, so we are going to have ln of absolute value of x plus ln of absolute value of c equals 1 over 2 times ln of absolute value of v squared plus 4. So on the left hand side we have ln of absolute value of x plus ln of absolute value of c equals 1 over 2 times ln of absolute value of v square plus 4. Now this 1 over 2 here becomes exponents on this, so we are going to have ln of absolute value of v square plus 4 all exponent 1 over 2, and then this simplifies to ln of the square root of v square plus 4. Okay, now on the left hand side we have ln of absolute value of x times c. So ln of x times c. Now because we have log on both sides, we do away with the log, so that we have xc equals the square root of v square plus 4. Now we know that y is equal to vx, so v is equal to y over x. So in place of v we have y over x, so that becomes y square over x square plus 4. Now at this point you can square both sides of the equation to do away with the radical, the square root. So that becomes x square c square equals y square over x square plus 4. Now since we have the denominator of this fraction to be x square, let's multiply both sides of the equation by x square. So we have times x square times x square. So this becomes x square times x square c square equals, we multiply x square across, x square cancels out x square, so we have y square plus 4 times x square, so 4x square. Now at this point c square is a constant. Okay, so let c square be equal to c1, which is also a constant. Therefore we have x square times x square c1 equals y square plus 4x square. Now we transpose 4x square to the left hand side, so that we have x square c1 minus 4x square equals y square. So we can factor out x square, so that we have x square c1 minus 4 equals y square, and then this is the general solution. Okay, this is the general solution of the differential equation. Now at this point you realize that we were given an initial value condition, that is y of 2 equals 4. Y of 2 equals 4. So per the initial value condition given, that is y of 2 equals 4, it means that x is equal to 2 and then y is equal to 4. So we are going to substitute the values of x and then y into this general solution, So we are going to obtain, now we have x square here, so that's going to be 2 square times 2 square c1 minus 4 equals y square, that is 4, so 4 square, y is 4, so y square is 4 square. Now 2 square is 4, so 4 into bracket 4c1 minus 4 equals 4 square is 4 times 4. So we have this cancelling out this, we are left with 4c1 minus 4 equals 4. We transpose negative 4 to the right hand side, so 4c1 equals 4 plus 4, which is 8. So we have 8 here, we divide through by 4, we have c1 equals 2. So therefore c1 is equal to 2. Now let's put in C1 into this general solution. Okay, so it means that we have x squared into bracket x squared times 2 minus 4 equals y squared. So we simplify this as y squared equals x squared into bracket 2x squared minus 4. So this happens to be the particular solution per the initial value condition given as y of 2 equals 4. So now let's move on to the last example. So in this last example, we are going to find the particular solution of the differential equation dy dx minus y over x plus cosec y over x equals 0 with initial condition y of 1 equals 0. Let's do that together. So we have dy dx minus y over x plus cosec of y over x equals 0. Now let's try to make dy dx the subject. So we transpose these two terms to the right hand side. So we have dy dx equals, this becomes y over x and then minus cosec y over x. Now at this point, let's try to find the LCM between x and then 1. So the LCM is x divided by x is 1 times y is y, minus x divided by 1 is x, then we have x times the whole of this, so that becomes, so notice that this is cosec, so it becomes x cosec of y over x, so that is equal to dy dx. Now we need to check if this differential equation is homogeneous. So what we are going to do is we are going to substitute lambda x in place of x and then lambda y in place of y for the two functions, both the top function and the bottom function. So for the top we have lambda y minus lambda x times cosec of lambda y over lambda x, all divided by lambda x. So here lambda cancels out lambda and then we have lambda y lambda x, so we can factor out lambda, so that becomes lambda into bracket y minus x times cosec of y over x, okay, all divided by lambda x. So we cancel out lambda, so we can say that is equal to lambda exponent 0, and then we have this function again, which is y minus x cosec y over x, all divided by x. Now you realize that this is equal to the original function here, and then we have the degree, which is exponent on lambda, to be 0. Now once dy dx is equal to this, then we say that this function is a homogeneous function of degree 0, and thus this differential equation is a homogeneous differential equation. So let's quickly clear this and then we proceed with the rest of the solution. Now what we are going to do is, let's try to simplify this. Okay, so we have dy dx equals y minus x. Now cosec is basically 1 over sine, so we have this times 1 over sine y over x, all divided by x. So let's simplify further. So you realize that this y is over 1. Okay, this y is over 1, so we can have y over 1 minus x over sine y over x, all divided by x. Now, the LCM between 1 and then sine y over x is sine y over x. So we have LCM sine y over x. Now, sine y over x divided by 1 is sine y over x. So we are going to have y times sine y over x, okay, minus this divided by this is 1. So 1 times x is x. And then we have this all divided by x. Now we can write this as x over 1. And then we are going to multiply the numerator by 1 over x, okay. So this x appears at the denominator here. So we can just write it as such, as x sine y over x. So that is equal to dy dx. So the next thing, we are going to substitute y equals vx, that is the first one, and then dy dx equals v plus x dv dx into this differential equation. So on the left hand side, we are going to have v plus x dv dx equals, on the right hand side, we are going to have y. Now in place of y, we have vx. So we have vx times sine vx over x minus x, all divided by x times sine vx over x. So x cancels out x, x also cancels out x. At the numerator, we can factor out x because it's common to both terms. So we have x outside, v sine v minus 1, all divided by x sine v. And that is equal to v plus x dv dx. So we have v plus x dv dx equals, x cancels out x, we are left with v sine v minus 1 all over sine v. Next, we are going to transpose this to the right hand side. So we have x dv dx equals, we have v sine v minus 1 over sine v minus v over 1. Now let's find the LCM. So LCM between sine v and then 1 is sine v. Sine v divided by sine v is 1. So 1 times the whole of this, that's going to be v sine v minus 1 minus sine v divided by 1 is sine v. So times v, that becomes v sine v equals x dv dx. So at this point, we have v sine v, we have negative v sine v. So this cancels out this. So we are left with negative 1 over sine v. So we have x dv dx equals negative 1 over sine v. Now let's transfer this dv to become denominator here. So that becomes x dx equals negative 1 over sine v dv. Now we flip both sides of the equation, and then we have dx over x equals negative sine v dv. At this point, we've been able to put all x's on one side, all v's also on the other side. So we are going to integrate both sides of the equation. So we are going to have ln of absolute value of x plus ln of absolute value of c equals, on the right hand side. Now, when you integrate sine v with respect to v, then you are going to obtain negative cos v. Okay, so this is this negative, and then when you integrate sine v with respect to v, you have negative cos v. On the left hand side, we have ln of absolute value of xc equals, this becomes cos v. Now, in place of v, we know that v is equal to y over x. Okay, so we are going to have ln of xc equals cos y over x. Okay, and this is called the general solution. This is the general solution. This is the general solution of the differential equation. Now, we were given the initial value condition, y of 1 equals 0. Okay, y of 1 equals 0. So for y of 1 equals 0, it means that x is equal to 1 and then y is equal to 0. Therefore, we substitute the values of x and then y into this general solution. So we are going to have ln of, we have x to be 1 times c, absolute value of 1 times c equals cos y is 0, x is 1. So this is equal to cos 0. Now, this becomes ln of absolute value of c. Okay, and that is equal to, now cos 0 is equal to 1. Okay, remember that the natural log has a base of e. Okay, so we are going to transport this to be exponent on e and equal to c. Okay, so we have e to the power 1 equals c, and thus c is equal to e. C is equal to e, the constant e. Therefore, we are going to plug in the value for c back into the general solution. So we are going to have ln of absolute value of x times e equals cos y over x. So this is called the particular solution per the initial value condition given y of 1 equals 0. So that's it for today's video. Thanks for watching and see you in my next video. Bye bye.